I'm inside the DAC. Consists of the old-fashioned R2R DACs. We can look here, for instance. This is a block consists of many DACs, 8-bit DACs, and it consists of the old-fashioned R2R ladder. And in this case, these blocks of DACs will generate this voltage range, who will be inside to create the weights of the neural network of the atomic triad. And this is only operational amplifier who will gain the impedance from high impedance here to low impedance before it enters the matrix. And in this block I decide to use the old-fashioned R2R DAC, who are fast, but of course in this case bulky. So I have the traditional shift resistor, and here I will control this by a Phoenix FPGA. I decide to choose I like to use a Phoenix FPGAs, in this case T120, and that's nice because it has so very fast turnaround cycle time to use the analyzer. In this case, of course, I will heavily use the logic analyzer in the FPGA, because I'm dealing with a lot of debugging in a measurement landscape between software and hardware, of course. So I expect that I will use a digital logic analyzer a lot. And a Phoenix seems to have, I have worked recent years with other vendors, but it takes a lot of time to rebuild the FPGAs. The Phoenix seems to be very fast to rebuild a new output bin files who I can load in the FPGA. It take, for the T100 I have run before this year, it take never more than 5 minutes to rebuild the whole FPGA, and then you have the fully integrated digital real analyzer instead of try to work with simulator. Actually, I have skipped use test bench and simulator most of the time because I simply not need to it. I instead use a direct analyzer, and it's very nice to work with the Phoenix tool in that case, in that specific case, because you spend so much time in debugging in the domain between software and hardware, often when you work with FPGAs and electronics in general. So I think actually the Phoenix tool is very nice. And the other nice thing I have understand is I like the low price of the silicon of the Phoenix FPGA as well. So I'm very happy that my friend advised me to start to test a Phoenix FPGAs. It's in my view a game changer. And the price of boom cost is also interesting, because before I think, oh well, FPGA is nice, it's the crown jewel when you work with electronics and development. But on the other side, classic microcontroller is much cheaper than FPGA. However, I have realized that a Phoenix FPGA seems to be much cheaper because they use the quantum, they call it the quantum method in there. I like that a lot. Fair enough, talk about Phoenix. This proof of concept will run at much slower speed than and if we imagine that we should in future build some ASIC, this is of course much bulkier, and the only purpose of this board is to check if it's possible to get the control loop to stabilize at all. My obvious question is, of course, will the principle work? That's the first question. And then where is the breaking point where you increase the size of the analog matrix so much that that you eat up all you use all the duty time for stabilization measurement instead of inference. I guess it's some sort of trade-off between the size of the matrix and the duty time of the compensation measurements in this architecture, because the obvious thing is of course if you increase your size of the matrix, you get the quadratic effects of the matrix number of multipliers compared to the overhead cost of the DAC and ADC at the rows and columns. Therefore, it's obvious that you gain power saving when you increase the size of the matrix. On the other hand, I expect that it will need more and more measurement to read the whole warped hardware distortion of the hardware, and therefore I expect there is a sweet spot of the savings of the power and on one hand, and the duty time of the adaptation measurements on the other hand. And that is probably also a difficult question to answer, even if you in this whole area. So I understand fully that, of course, if we could create materials that are analog domain but flawless, that would be great. But I think for the moment we need also some sort of control system to control an adjustment in full analog domain to compensate the flaws of the analog calculations. You can of course find all the information at my repository, and you find the status of the PCB in this folder, and you also find all the documentation and so on in this, and you will find an audio book as well here, but you can also look at my YouTube channel. I will put the link in the description, of course. And here you see the pattern of 3D step of this board. It looks like this for the moment. So here you see all the ducts is located here, and the triad matrix there, and you get here you see the operation amplifier before it entered the ducts, before it entered the matrix. And here you see all the components I have not yet placed. This is all the components for the columns, and here we have the FPGA and control logic. I expect I will design this on a 6-layer board with 3 ground planes and 3 signals layers. So top and two mid layer will be signal layer, and bottom layer will be ground layer, and then layer, and then 2 more a layer for ground in the layer. When I talk about ground layer, I would prefer to not use bottom layer like this, so I will replace, for instance, this and try to minimize the area of ungrounded area at the bottom, because my idea is bottom layer, these layer, and these 3 layer will be the ground plane, and these layer will be signal layers. That's my stack up, because that fits that use like this. So when I talk about it, I will do like this instead, and use for vertical lines I will use like this instead. So I hope I will not be so very reduced with the impedance match, but instead, because it's so slow, I mean, I run at 500 kilohertz and it will ring out, and hopefully everything in the signal when I run the Hugmark code will be ring out and be settled to a steady state before I read off my signals of the matrix. Well, that's for now. I hope you follow me up, and stay tuned.